Hello everyone. Today we are going to discuss about armature reaction in DC motor. In previous class we discussed about back EMF and its significance, and also we discussed about the difference between DC motor and DC generator. On that time we concluded that there is a motor action in generator or there is a generator action in the motor. So the generator action in the motor is nothing but a back EMF. Let's discuss about some practical phenomena which is very close relative to armature reaction. So if you are understanding this concept, then we can easily understand the armature reaction. Practically, in magnetic applications, we can use the magnetic sensor to detect the vehicles. If you put one magnetic sensor on the road, if any vehicle cross that magnetic sensor, it will sense that and it will make sound. The phenomenon is due to that earth magnetic field, whenever the vehicle crosses that magnetic sensor, that magnetic lines, earth magnetic lines will be distracted. So this is the figure shows the magnetic sensor and vehicle detection method. So this is the magnetic sensor. So this black color is the magnetic sensor, and this dotted line will be the range of that magnetic sensor. So within that range, this sensor will detect. These lines are called earth magnetic lines. Earth magnetic lines or earth magnetic field. So initially those lines will be in straight line. In the second figure, whenever the vehicle reaches to that magnetic sensor, the frame is metal frame, whatever it is, which will affect the magnetic lines. Okay. So whenever the vehicle reaches to magnetic sensor, these magnetic lines will start disturbing. So whenever the vehicle reaches to a complete area loki a vehicle వచ్చినట్లయితే all the magnetic lines will be disturbed. Then the magnetic sensor will sense that signal and give the signal to the speaker. So here we have to understand earth magnetic lines are affected when other magnetic material comes nearer to it. In the similar way, we can observe in the DC motor the effect of armature flux on the main field flux. We already discussed about the back EMF in DC motor. Whenever the load connected to the DC motor, that armature will start rotating. That rotating armature conductors will cut the magnetic lines from north pole to south pole. Then the EMF will be induced. That induced EMF is nothing but a back EMF, which is opposite to the supplied voltage. When the EMF is induced in the armature, the current will pass through that conductors automatically. If the current is passing through that conductors, that magnetic field will be created. That is called armature MMF. That armature MMF and that magnetic lines from north pole to south pole, that is called field MMF. So the effect of armature MMF on the field MMF is nothing but a armature reaction. What happens if both are mixed? The resultant magnetic field will be not same as previous. Now we are going to discuss about that armature reaction. What happens if both are mixed? One is armature MMF, another one is field MMF. So there are two MMFs. One is armature MMF and another one is the field MMF. Let armature MMF be FA, that is armature EMF. Let FF be field MMF. So the effect of armature MMF on the field MMF is called the armature reaction. So the resultant MMF or the magnitude of the resultant MMF will be reduced. So armature MMF weakens the field MMF. let's see how it will weakens the main field MMF. There are two axes. One is GNA, nothing but geometrical neutral axis. This GNA, geometrical neutral axis, is GNA is the line passing through midway between any two magnetic poles. So from this I can write, suppose this is the magnetic poles, north pole and south pole. In between there is a armature, there are brushes, you can have conductors. So GNA is a line passing through midway between any two magnetic poles. So but this is the midpoint, these are the magnetic lines. From the definition we can have GNA is the line passing through midway between any two magnetic poles. So ఈ మధ్యలో గుండా పోయే లైన్స్ అయితే, so I can take this as a GNA, geometrical neutral axis. So another one is MNA. This MNA is nothing but magnetic neutral axis. This is the line passing through the region of zero flux existing between poles. So we have to consider there are two axes. One is GNA, another one is the MNA. Geo-neutral axis is the line passing through midway between any two magnetic poles. So I have taken this as a GNA. So when the load is not connected, so armature is at stationary, there is no armature MMF, only field MMF is existed. This MNA is also at the same position, MNA. Why? Because at this point the magnetic flux is zero. So as the definition, magnetic neutral axis is the line passing through the region of zero flux. So if this magnetic flux is having in this fashion, that MNA, so this is, and this is called MNA. Why? Because at this point zero flux. If I take on x-axis it is b or phi, so at each and every 0 point this is MNA, and you can also MNA, and it is also MNA. So here the magnetic flux is 0, so the line passing through these points is also called a MNA. So from this we have to understand, when the load is not connected, that means armature MMF is 0, only field MMF is present, then the angle between the MNA and GNA is 0. At no load, angle between MNA and GNA is equal to 0 degrees. So when the load is not connected, MNA and GNA are at the same position, and the angle between the geometrical neutral axis and magnetic neutral axis will be 0. Now consider when the load is connected, what happens. So if you see here, there are three figures. The first figure, suppose figure A, it will be figure B, and it will be figure C. Figure A shows when the field MMF is considered only, and figure B shows when the armature MMF is considered only. Figure C when both armature MMF and field MMF are considered. So if you see in figure A, if the only field winding considered, the lines will be straight line. In figure B, when the only armature MMF is considered, that is on load. So on load condition only the armature will start rotating. When the armature starts rotating, the back EMF will be created. That due to that back EMF, there is a magnetic flux surrounded by that conductor. So these are the conductors in the armature. So the cross mark is nothing but the conductors, the current flowing through these conductors will be away from the observer, and dot marks, so this symbol indicates current flowing away from observer. This dot indicates towards the direction of magnetic MMF will be known by using right hand thumb rule. So if you place our thumb in the direction of current, the folded fingers will give the direction of magnetic MMF. Suppose if it is cross mark, then I can write the magnetic field around this cross mark will be the clockwise direction. Why? Because away from the conductors, then folded fingers will be gives the direction of magnetic field, that will be in the clockwise direction. For the dot conductors, the magnetic field will be in the anti-clockwise direction. So the same can be explained here. So for this conductor, the magnetic field will be in this direction, and for this in this direction. So this is FR and this is field MMF FF. In the figure C, when the both FF and FR considered, in the figure C both main field flux and armature field flux are considered, this main field flux will be distorted in this way. So initially there is a straight lines. This is from North Pole to South Pole. Now these lines will be distorted in this way. So when the lines are stationary or straight lines, the G and A and M and A are the same. Why? Because M and A is the line passing through that points where the flux is 0. So I take it as these 2 points. So when I consider here GNA is in this position, and now because of this distortion, these positions are taken as a 0 flux points. Now the MNA will be shifted in this way. So in this figure it is explained here. So this is armature field flux, and the resultant will be given here. Because of this, MNA is shifted in this way. Figure A, we can have this is GNA or MNA. This is FF, field flux or field MMF, and it is making 90 degrees. Next, figure B shows this is GNA and MNA. This is called, if it is a 0, it is GNA and MNA. This will be FR. So armature MMF. For figure C, we have to show the resultant. So this is GNA, this will be FF, and this will be FR. So angle between FF and MNA is equal to 90 degrees. Here the resultant magnitude will be, this is the resultant, that is called resultant MMF, the vector product of these two, and with this we have to draw a 90 degrees MNA. So this is MNA making 90 degrees to the resultant MNA. So the phase shift from GNA to MNA is nothing but alpha. Okay, with this we can understand when the load is connected, the armature MMF weakens the main field MMF by shifting this MNA. Because of this shifting of MNA, the commutator actions will be disturbed, and the brushes, the collection of power, some sparking may be occur. Okay, so for basic electrical engineering up to now this is enough. So if time permits, we will discuss about those other things, how commutation process will occur, how the brushes will be shifted, what is the remedies for armature reaction. We can discuss in the further classes. But for basic calculation, this is enough. Now let's solve a problem on armature reaction and speed regulation of a DC shunt motor. A 440 volts 4-pole lap connected shunt motor has no load input current of 15 amperes and shunt field current of 10 amperes. At full load it takes current of 150 amperes. So there are two conditions, one is at no load and another one is at full load. So if armature resistance 0.1 ohm and flux per pole on no load 0.05 webers. And number of armature conductors will be 750 and contact drop per pole brush is equal to 1 volt. So assume the main field flux affected by armature field flux by 1.5 percentage. Yes, this is armature reaction. It is at full load. Here we are having no load and full load conditions. So at no load they given as I0 as 15 amperes and at full load they given 150 amperes. And flux at no load phi naught is 0.05 webers and flux at full load is they given as 1.5 percentage weakens by 1.5 percentage. Now I can write 1 minus 0.015 times phi naught. Why? Because it is weakens by 1.5 percentage. So from this I can write 0.985 times phi naught. And other terms are constant whether it is no load condition or full load conditions. The supply voltage will never change, 440 volts, and the shunt field current ISH is never changed, is as 10 amperes, and number of conductors Z 750, and armature resistance 0.1 ohm, brush drop is equal to 2 volts, 1 volt per brush. So there are two brushes, we can take it as a 2 volts. Now what they want to calculate no load speed and full load speed. So for no load speed I can take a naught as no load speed. This is at no load. Let's calculate back EMF at no load. EB naught is equal to V minus IA naught RA minus brush drop. And no load armature current IA naught is equal to no load current minus ISH. So no load current as 15 amperes minus ISH as 10 amperes. Now it will be 5 amperes. Substitute this in above. You can calculate no load back EMF 440 minus 5 multiplied with armature resistance as 0.1 ohm and brush drop 2 volts, and this value is approximately equal to 437.5 volts. 5 volts. But they want to calculate no load speed. So I write E naught is equal to no load speed multiplied with phi naught Z upon 60 into P by A. Now it is 437.5 volts is equal to N naught. No load flux will be 0.05 multiplied with the number of conductors 750 upon 60. Number of poles will be 4 and lap connector, so number of poles and number of parallel paths are equal. Now it will be 5. From this I can calculate no load speed is equal to, first question, no load speed is equal to 6 688.73 rpm. Now the second question is full load speed n. Full load back EMF EB is equal to V minus IA RA minus breaststroke, and full load armature current is equal to full load supply voltage minus ISH. Now what is full load supply voltage, supply current? They given as 150 amperes. So I can write 150 amperes minus 10 amperes. So shunt field current is 10 amperes. Now armature current at full load is equal to 140 amperes. If I substitute this armature current here, full load back EMF is equal to, what is supply voltage? 440 volts minus armature current 140 amperes multiplied with 1.1 ohm minus breaststroke's 2. So from this I can write back EMF, full load back EMF is equal to 424 volts. Sorry, so if we calculated here, we can have approximately 700 rpm. So no load speed is 700 rpm. Now from this I can calculate full load speed n. So from this I can write EB is equal to n phi z by 60 into P by A. From this I can calculate n as 688 rpm. Now the third question is speed regulation is equal to no load speed minus full load speed upon full load speed. So no load speed is 700 minus, no load speed is 700 minus full load speed 688 upon 700. If I want percentage regulation, speed regulation is equal to, I have to multiply with 100. I can have this speed regulation 1.637 percentage. So at no load the motor runs with 700 rpm. When the load is increased and reached to full load, the speed is reduced to 688. The 12 rpm is the difference with respect to full load 700 is the speed regulation, right? With this we can calculate no load speed and full load speed when the armature reaction effect is considered. So because of armature reaction at full load, this flux will be weakened. Initially it is about 0.05 webers. Now it is reduced to 0.98 times phi naught. Right? Now the flux is weakens. So with this we completed problem on armature reaction. Thank you.